Today we will be looking at mixtures of strong acids and strong bases. And the key thing here is that when we are looking at mixtures of strong acids and bases, you can either have excess acid, in which case the solution is acidic, or you can have excess base, in which case the solution is basic. And finally, you can have an exactly equal amount of acid and base, so neither is in excess. So neither the acid nor the base are in excess. And if that's the case, our pH is going to equal 7. Okay? If we have excess acid, we're going to have our pH less than 7. If we have excess base, our pH is going to be greater than 7. Okay, so by excess acid, of course, we are meaning excess H+, and by excess base, we are meaning excess OH-. Okay, so let's start with a really simple question. So for example, 10 milliliters of 0.10 molar HCl, a strong acid, monoprotic strong acid, is mixed with 10 milliliters of 0.10 molar NaOH. And feel free to pause the video at any time if you need to copy stuff down, obviously. All right. So what we've got here is we have a certain amount of acid and a certain amount of base. Both are strong. So for our acid, what we can do is we can calculate the moles of H+. Okay, so that's going to be equal to the moles of HCl, which is 0.010 liters times 0.10 moles per liter of HCl. And then we know that there is 1 mole of H+ for every 1 mole of HCl. This would be different if it was a diprotic acid, for example. Okay, and that is going to give us 0.0010 moles of H+. Second thing we're going to do is we're going to find the moles of OH-. Okay, so that's going to be equal to the moles of NaOH because there's 1 for 1. So we have 0.0100 liters times 0.10 moles of NaOH per liter times 1 mole of OH minus for every 1 mole of NaOH, and we get 0.0010 moles of OH minus. Now, if you haven't noticed before this, these are identical. You could probably see that from the question. And if they are identical, then when you have the reaction between the H plus and the OH minus, and we get our H2O, we're going to do something that's a little bit like a race table, but it's not going to be a race table. It's going to be a Ricuf table, because we have R, which is our reaction, the initial, and this is going to be moles, not molarity this time. And we're going to have the change in moles, and we're going to have the final moles. So it's a little bit different. It's not molarity, like a race table would be, and it's not an equilibrium amount because we don't have an equilibrium reaction here. We have a one-way arrow, okay, one-way arrow there. So our initial moles of hydrogen is, just make sure we check on that, okay, so we have 0.0010 moles of hydrogen. I don't want to write the moles, it's going to get in the way. There we go. And we're going to have 0.0010 moles of hydroxide. And hopefully you can see that this is a 1-to-1 ratio, and we will have both of those reacting completely. So we're going to use up all of our hydrogen, and we're going to use up all of our hydroxide, and we are going to end up with, well, the water didn't start at 0 because it's the solvent, but we'll just put like a blank there, and it's going to go up by 0.0010 moles. So left over at the end we have, let's see, 0 moles of H plus left over. We have 0 moles of OH minus left over, and everything has turned into water, which just would become part of the great water pool, okay? Because of course it is the solvent. So what is the pH then if you have 0 moles of H plus and 0 moles of OH minus left over at the end? And this is easier than you think. So pause for a second and think about it. And you have no excess acid and no excess base. So the solution is neutral. And if it is neutral, then the pH is 7. Gosh, that was long and involved for such a simple thing. I hope you listened to that on 2 times speed. Okay, let's try one that's not quite as simple. So, example. If 10 milliliters, 10.0 milliliters of 0.100 molar HCl is added to 90 milliliters of 0.100 molar NaOH, is the pH of the mixture? Okay. So in this case, we have our HCl, which is going to give us hydrogen. And we have our NaOH, which is going to give us OH minus. So let's calculate the moles of H plus. Moles of H plus. And in fact, I'm working in millimoles. I can't help it. It's just so much easier. Okay, so we have 10.0 milliliters. Just remember that milli is just going to hang out. It's not going to get canceled. It'll come back at the end. Okay, times 0.100 moles per liter of HCl. And remember, there is 1 mole of H plus for every 1 mole of HCl. Okay, so now the math is easier than before and we don't have as many zeros kicking around because 10 times 0.1 is just 1. So we have 1, and let's watch our units cancel. Moles of HCl cancel out. Liters cancel out, but notice that the milli is still there and the mole is still there. So we have 1.00 millimoles of H plus. Now we're going to calculate the millimoles of OH minus. Okay, so we now have not 10 milliliters, 90 milliliters, 90.0 milliliters times our concentration is 0.100 moles of NaOH per liter. And there is 1 mole of OH minus for every 1 mole of NaOH. Okay, so we will end up with 90 times 0.1 is 9.00 millimoles of OH minus. So I'm hoping that at this point it's really obvious to you that our OH minus is going to be the reactant that is in excess. But let's just write out our equation just in case. Okay, so we have our H plus OH minus. This is the net ionic equation for any strong acid, strong base reaction. Oh, that was supposed to be blue. And we get one H2O, H2O. Okay, so we are starting with our ICE, and in this case, this is going to be moles, initial change in moles, and oh, not E, that is going to be an F, because that's going to be our final moles. Okay, so we're starting with 1 mole of H plus, and we're starting with 9 moles of OH minus. And they react 1 to 1, and we're going to have to use up the smaller one first because this 1 to 1, this is just easy stoichiometry. So we're going to use up all of our hydrogen, right? And that's going to leave us with 0 moles of hydrogen. And if only 1 mole of, if only 1 mole of reactant, millimole. My apologies, these are all millimoles. There we go, millimoles everywhere. 0 millimoles. Okay, and if we're using up 1 millimole of H, we are also going to be using up 1 millimole of OH minus. And that's going to leave us with 8 millimoles of OH minus left over. So that is OH minus is in excess. So if we were just asked if this solution is acidic or basic, we would say yes, it is basic. But if we're actually asked for the pH, we need to go a step further. We need to say, in order to find pH, there's a couple ways to do it. We could start from our concentration of hydroxide. We can use hydroxide concentration to find POH, and then we could use that to find pH. Or we could use hydroxide ion concentration, and we could find concentration of hydrogen, and we could find the pH from there. But both of these need us to have the concentration of hydroxide, and we don't have that yet. We just have the millimoles of hydroxide. So let's start by finding the concentration of hydroxide. Concentration is equal to the moles per liter, and we know the millimoles of hydroxide, 8.00 millimoles hydroxide. Okay. We're going to go back here, and we're going to say, oh, what is my volume? Well, hang on a second. I added 10 milliliters of the acid to 90 milliliters of the base, which means I'm going to have a grand total of 100 milliliters total. Yeah? So that leftover hydroxide is going to be in 100 milliliters total volume. So we'll put that down here, 100 milliliters. And do you remember I said that the milli would come back around again? Well, look, here it is. We have a milli here, and we have that milli there, and those are going to cancel each other out, and we're just going to be left with moles per liter, which is kind of nice. So now I just have 8 divided by 100, which is 0.008 molar hydroxide. Okay. And now, second thing we're going to do is we're going to find the POH. Pause the video and write for yourself the POH formula. I'm going to write the POH formula. It is the negative of the log of hydroxide. Okay, hydroxide concentration. So that's going to be the negative of the log of 0.00800 molar, which is 0.008 log. That's 2.097. And then our pH, take a moment for yourself and write the formula for pH. I'm going to write the formula for pH, getting it from POH. So that's going to be 14.00. Don't forget your 0.00. And that's going to be minus the POH. Okay, so that's 14.00, which is your PKW, minus 2.097, which is 11.903. Now I have to take a quick look at my sig figs here because I think I've done something maybe a little goofy. I've got up at the top, I've got 3 here, I've got 3 here, Oh, I got 3 everywhere. So what I should have done is down in here, this should have had an extra 0 because remember the significant figures for any p-value, pH, POH, pKw is always after the decimal. So there is our final answer to 3 sig figs. Okay, and I'm going to show you that was root number 1. That was going from the OH to the pH, POH to the pH. Now we're going to go the other route just to remind you of how those formulas work because it's been a while probably. So alternate step 2 and 3, maybe I'll draw them in red. So alternate step 2, we're going to find our concentration of hydrogen, and we're going to use that from concentration of hydroxide. So pause and write for yourself how you find the concentration of hydrogen if you know the concentration of hydroxide. Okay, so pause and do that. Okay, and so we now have Kw over concentration of hydroxide. Because if you remember, Kw is equal to H times OH. Okay? So that's going to be 1.0, but I want 3 sig figs, so I'm going to put 1.00 times 10 to the negative 14, that's our Kw value, over, and we'll go back and see our concentration of hydroxide, 0.008, 0.008 molar. So 1 times 10 to the negative 14 divided by 0.008 is 1.25 times 10 to the negative 12 molar. Okay, and we're going to do a second one here, or second step rather, and that molarity that we just calculated was molar H plus. And so now we need to find the pH, which is the negative of the log of concentration of hydrogen, and then that's going to be negative log of 1.25 times 10 to the negative 12, and that equals, hopefully it should be the same as our other answer. Oh, look, it is, yay, 11.903. 11.903, and we are done. Yay, happy day. Whee. Okay, I'm going to pause our video for a moment. Okay, so yeah, that felt really long to me. So what I'm going to do is I'm going to stop the video here, and I will post this up along with the worksheet, Mixtures of Strong Acids and Strong Bases, and you can do the first 2 questions. Okay, so you'll have a worksheet, whoops, called Mixtures of Strong Acids and Strong Bases. And you can do questions number 1 and 2. And I will come back and teach you stuff with some diprotic things in a little bit, but I'm tired for today, and I imagine you are too.